So in this experiment, anything can be faulty. It can be the Pasco sensors, the multimeters, the analog voltmeters, ammeters, the power pack. And so we're going to take lots of measurements and double checking of everything. So here we've got first the manufacturer's coding, which is a red, violet, brown, gold. So if you look up the chart, in a previous lesson, you'll see that gives you 270 ohms plus or minus 5%. So the calculation on that is 270 times 0.05. And so there's 13.5 ohms plus or minus on that. So the range for this particular resistor will be 256.5 to 283.5. So that's what the manufacturer says we can get on it. We can also test that with the multimeter. So you click on the ohms region. So there's always one on the COM, and then put the other lead onto whatever it is. So you can see the ohms, so onto the resistance there. And if you can go to that, you can see that that gives us 265 ohms. So that is pretty close to what we want. It's well within the range. So that's all good as well. And then we're doing really the experiment, which is to measure the resistance using Ohm's law. So we're going to use voltage, going to take voltage measurements and amp measurements. Now you can see that on the machine we've put 4, but the multimeter actually says that we have, so 3.93 it is, volts. And the ammeter there, when we zoom in, it's giving us 14 milliamps. So that is only, it's on the 50, so it's 14. A bit hard to read as well. So that's actually just 0.04 amps. And so if we do the calculation, so rearrange V equals IR to R equals V on I. And so 3.93 divided by 0.041 amps gives us 280.7. And that too is within the range. It's a little higher. So that's all of those readings are very good. And all those double checks are very good as well. So to complete the experiment, we're going to use a couple of resistors and we're going to test them on a range of voltages. So the power pack is going to give us hopefully ups and twos, but we're using the multimeter to give us the values on those. And the ammeter, we're going to take those readings as well. So you do that a couple of times, a couple of trials. So range of 5, repetition. And then you can change the resistor and see the effect of different resistors with V equals IR. So this next section is quite long and I'm not going to speed through it. I'm just going to let you use your own jumping back and pausing and replaying. So this is the raw data that I got from a student. I think I have tidied it up a little bit, but we need to tidy it up a heck of a lot more. And so the first big thing we need to do, well, I'm doing quite a lot of things here. So first of all, get all the headings right. So using the right symbols, so insert symbol, so find the Ohm sign and press insert. I've missed that there, but I'm not going to re-shrink it down. And so that's 200 ohms, 400 ohms, and then I realized, well, you just generally, everything clear and concise, so don't try and repeat everything, so I should just put ohms at the top. So I'm just getting rid of that. And so I've got that there. It's going to look, you're going to jump ahead to 8 minutes and something if you want to see what the final product looks like. But I need to get all the amps and voltages together. So I'm just copying and pasting over there. Just delete that out. So get all the amps together and get all the volts together. So just deleting those columns. So this data is pretty good. Range of 5, range of 5, repetition of 3. Even better if you've got a range of 5 different resistors with 5 different voltages and then 5 repetitions. That would be perfect. But this repetition of 3 is quite fine, and range of 3 is quite fine for this. This is just year 9. And so I'm making some room for the average, which is the value we're going to use for the graph. And I'm also making some room for absolute uncertainty of the mean. Now, after I've done that, I will go to the instrument uncertainty. I can't remember this data, whether we used analog or digital. So I'm just going to apply a digital error, which you'll see very soon. So for the time being, Usually there's quite large variations. So normally absolute uncertainty of the mean is the larger one, and we take that one. But then I discovered actually that's actually quite small. So what I'm doing now is just cleaning it up. So I just pressed center and center up and down, left, right, horizontal and vertical on all the data, just to make it neat. And I'm just bolding everything except for the entry data points. And now I'm just neatening everything up. So that voltage is merge cell, so that goes across the whole thing. So I can merge across a row and down a column. At some point, I'm going to realize I've got one too many lines. So I'm going to just click and unmerge and then delete one of those. So I don't need 3 lines in the heading. So if it doesn't fit, you can either stretch it out a little bit, or you can wrap text in the center top. You'll see me do that soon, or you can drag it down. So right now I am just getting the voltage and currents together. So I've got those down there. Now everything needs to have the same number of decimal places, or sig figs, or decimal places. So that one's to 3 decimal places, so I play with that button. Just going back and making sure everything's centered again. And now I'm trying to get that so I can read the whole thing. So merging will widen it for me. I think right now I've realized I don't need all those volt ones, and I just basically don't need 3. So I'll just grab that and delete the third one. So to delete it, you can't, it's going to just, if I try and delete it, I'll lose that whole power pack register thing. So I need to unmerge it by pressing merge again. Then I can delete out that row and pull all the cells up. Now I can go back and merge those ones again. Okay, so now that's a little bit cleaner. So I'm just dragging those to make it fit. That there is the left Alt plus Enter. If you want to know how to press Enter within a cell, you can't see me do that on the keyboard. So that's a trick to get a different line within the same cell. This one I'm just going to widen it and then wrap it, and just to get it to fit. And now it fits. All right. And I'll just do the same thing over there and just widen it and make it a bit deeper. Now I'm just putting 1, 2, 3, assuming you know it's trial 1, 2, 3. And now I think I'm about ready for the calculations. So calculations, you go up. Oh, that's missing. That's unfortunate. So I'll have to shrink that back, and you can see that, and you'll have to pause that. And then you copy and paste it all the way down, and then you can copy and paste it all the way down as well. And make sure the decimal places are the same again, and copy that down. So the decimal places are all the same. Next, we will absolute uncertainty of the mean. So the absolute uncertainty of the mean is the highest value minus the lowest value divided by 2. And so the algorithm for that is max, and then you grab which lists you want to get the max from, and then the list which is the same to get the min from, and then divided by 2. So you can pause it and type in that algorithm. And once you've done that, adjust it for the right number of decimal places and copy and paste it down, and you're done. And you can do the other thing on the other side, but you need to have different number of decimal places. So you just adjust. You can just do it like that. I'll have to adjust for decimal places too. So that is 3 decimal places, pressing that button over there. Okay, so that is the table. You just copy and paste that if you're doing a science report. And now we're going to look at how to do the graph. So first thing you need to do is, because you need to change it. You need to change, so normally the independent variable is what you change is on the x, is on the bottom of the graph, and on the y is what you measure. But we're swapping them around because In order to get the gradient to be the resistance, we need V on I, and V on I is delta Y and delta X. So therefore, we need to swap them around and have the independent, which is V on the Y-axis, and the dependent, which is I on the X-axis. So we have to swap them around and do it the wrong way, both in the table, which I'm not going to paste, but I'm going to use to make the graph here. And so that there, I've just insert scatter graph. I'm going a bit fast here, so you'll have to rewind and listen to me at the same time. So now the gradient is the resistance. So that's why we put them on the wrong place. The independent dependent variable, we swap them around so that it matches the equation. Now, just to get those series to be the right thing is quite annoying. So you have to go here to the data sets and edit them. But also you need to have a symbol saved away, which I didn't do. So I need to close that down. See, I can't just type in, I need a symbol. So there's a few tricks there. So I'll close that down and do it again. I need to find out where the symbol is. So there's a symbol there that I can just grab. So copy and paste that. Control C, Control V for copy and paste. And then I go to the series, edit it, and there I can type in and Control V for and it'll throw up this symbol for me. And you can see it works down there. Okay. And so I just need to fix the other ones too. So just repeat that process. So there we go. And then left mouse click or right mouse click on that button. It does go through 0. So when the current is 0, the volts should be 0. When the volts is 0, the current is 0. So I do set the y-intercept to 0. Put the equation on the chart, which is it's y equals mx. So the number is the actual value of the resistor, and r squared, just in case you want to talk about how well it fits, the dots fit the line of best fit. And so you need to just repeat that for all three, and that equation is actually giving you the value of what the resistor is. Now, this data seems to be nowhere near as good as the introduction video that I set up for you. This data is a couple of years old, so I can't remember exactly if it was done with the same instruments. Probably not, because it's a bit of a struggle to find any instruments that work. And I'm just deleting out the bits I don't like. So I'll get rid of those lines. Apart from that, it's pretty much done. Now, the last thing you need to do is error bars, which is the reason we did absolute uncertainty of the mean. So that graph is not looking too bad. All right. And so this one's the trickiest bit to do. So add error bars is one way to do it. So that adds them somehow, but you need to make sure they're correct. So if you double click on those, there's the vertical ones I've clicked on so far. I need to double click on, or it's not working, I'll just do a left mouse click. And that'll say edit error bars. Usually if you double click it, it comes up on the right hand side. So format error bars. The value that we are using is a range, and so you need to put the range in there. So you need to go to where that absolute uncertainty of the mean is for the correct resistor, so the blue one, and highlight that, and that's the amount that'll be above. And then you need to make sure that looks exactly the same. So Control C and then Control V, and that is the correct vertical, vertical error bars. And now you need to do the same with the horizontal. So click custom, specify value, find the correct range. You can just highlight it and it comes up, but then it doesn't do it that easily in the second bit. So in my experience, you're best highlighting the top bit, going to the bottom, deleting it, and then pasting it, and then you get it. Now you can see the error bars are too small to be seen. So you must know that they're there. So I'll do a text box in a second saying error bars too small to be seen, even though I can see one or two of them. And you need to go forth and do that for all of them. Now, this is going to be the normal way to do things because normally there's such a large random error that you will see some nice error bars there that are going to show up and help you interpret your data. So absolute uncertainty mean is the way to go. Now, because they're just non-existent in this case, I will continue on in a second to show you the second way you do it, which is using instrument uncertainty, which lucky in this case doesn't require uncertainty propagation, but in the future it will, which is another trick you're going to have to learn. So same thing, copy, delete that out, paste it. Have to do this several times. One more time. So that's not coming up automatically. Left mouse click, custom verify, specify. And paste and OK. And last one. Now, if this was the largest, if this was the greatest uncertainty, this absolute uncertainty of the mean, you would be done if you're just adding the text box in saying that error bar is too small to be seen. But that's not the largest uncertainty. The instrument uncertainty is larger. So I can't see any of these error bars, which is not good. It's showing me that there's definitely some accuracy issues because the range error bars, the line of best fit doesn't go through the error bars, which is of concern. So I'm just checking that those error bars make sense. And then just finishing it off. So they seem to make sense, although it doesn't really make sense of the data because they're not perfectly on the line. So putting in the insert text box. You could also write that if you put this in your report and put figure 1, graph of whatever bracket, then you could put it brackets. It's a little safer to do it here. Error bar is too small to be seen. And I think I wrote vertical. Oh no, that's coming up in the next one. All right, so because that uncertainty is not the largest, we have to also consider the instrument uncertainty. And because I can't remember whether this was analog or digital, if this was analog, I'd be taking half the smallest increment. But I know at least there's digital voltmeter at the start, so that is the smallest digit. And so we have to fix everything now because now the voltage, we're putting the instrument uncertainties. Now we really should do that anyway. Even if the absolute uncertainty of the mean was the larger one, we should really put plus or minus voltage and current up in the top there, and then write a statement saying absolute uncertainty means larger, so we'll use that. But in this case, this instrument uncertainty, which I'm assuming is digital for both, and I'm just putting the smallest digit, so 0.1 plus or minus 0.11 volts and 0.01 amps, and then just cut and pasting to correct that. So now it's a little easier actually because now I can just use a fixed value. So I just click on the fixed value. That one's already correct. And the only thing I have to fix is the vertical error bars. Now I can't see them. So in order to correct that, I'll just restart all over again. So I just get rid of them and then put them back, and then I get those large incorrect ones. So everything in this is sometimes a little fidgety. There's little quirks, unfortunately. With computers, it's always like this. And so I'm just doing a quick fix on all of these. The vertical ones are all 0.1. So left mouse click, not working. Left mouse click, format error bars, fixed value, 0.01, that's all correct already. And then just correcting. So 0.1 for the vertical, which can't be seen, and 0.01 for the horizontal, which can be seen. And now it's way better as well, because now the line of best fits go through the error bars, which makes sense. And so with the text box, I just say, so the horizontal bars I can see, but then there's a question, did you do the vertical error bars? Yes, I did, but I can't see them. So you need to tell me that. So you need to write vertical errors bars too small to be seen. And so that is actually the finished product. And so you can copy and paste that graph into your report if you're doing this for a report. And the last thing we need to do is describe that. So just go to the video here on how to describe graphs. This one is directly proportional. So as current increases, voltage increase, or voltage increase, current increases. And also describe the gradient. So as the resistor increases, does the gradient get steeper or less steep? And what does that mean? And make sure you back it up with data values as well. And you can give the equations of the line as well also.